to Astrobiology online course at the center. I was delighted to see so many students join in from around the world, so many participants, and I'm sure the others who haven't yet had a chance to go through the recording, we have shared the link in case you have any problems. We will be sending out another email later today or tomorrow, which will have more detailed information as to how you can find the previous recordings. But today is our second day and the part two of yesterday's lecture on the making of a habitable planet. And we have with us Dr. Afshin Khan, who's joining us from California in US. And I'm very pleased to introduce her. She's a dear friend of mine. So Afshin is an astrobiologist, a research scientist at Blue Marble Space, and a postdoctoral scholar at NASA JPL. She has an interdisciplinary background. She graduated from Washington State University with a PhD focus in geomicrobiology and astrobiology. She hails from Jamshedpur in India and completed her undergraduate education at Bangalore University. Prior to that, subsequent to that, she moved to the United Kingdom to pursue a master's at the University of Nottingham. She worked at the European Molecular Biology Lab in Heidelberg, Germany, and at German Aerospace Center DLR in Berlin before moving to the United States. Afshin likes to use the educational background she has in biotechnology towards astrobiology and space exploration, and she learns new skills along the way, and she loves science communication and outreach for STEAM. She's also a co-founder of a protein biotech startup in the US and has over 8 years of teaching experience in Earth and planetary science. So Afshin, I am immensely delighted and honored to have you with us in these challenging times. I'm aware that California is in right now and everything that's going on. It's really overwhelming to see such support coming in from all places. So the floor is all yours. We'll have you speak and then we can have the question answers right after that. So feel free to take over.
All right. Thank you, Sid. Thank you for the kind introduction. And I just activated screen share, so someone will have to confirm if you can see my screen and if it's on slideshow mode, if it's like full screen.
Yes.
All right, so good morning to everyone in India and everywhere else where it's still morning. It's late evening for me here in California, and I really appreciate everyone joining in from around the world. I am really excited to continue John's lecture from yesterday. I do have big shoes to fill in. He set the bar very high for the rest of us. So we'll continue our discussion on making of a habitable planet, and we look more at plate tectonics. And yesterday I noticed a lot of you were very curious about plate tectonics, what it is, how does it work? And so we'll discuss all of that today, and we'll look at where plate tectonics is happening, besides Earth, if we have any evidence in other planetary bodies having plate tectonics. And how is plate tectonics important to life? So I should tell you that when I was teaching geology for 8 years or more than 8 years, plate tectonics was my favorite topic to discuss with students. I just love talking about it so much that this is the reason why I chose this topic to talk about in this workshop. So I have already been introduced, so I'll move on to the next slide. The key concepts that we'll talk about today is what is plate tectonics, just in case for students or for those of you out there who do not know what it's really about. Okay, you keep hearing about this interesting term and we know it's real, it's a fact, but what is it and how does it work? And how was it discovered? Like, how did scientists and people come to understand that this is happening on our planet? We'll talk about what powers plate tectonics and what are plate boundaries and what's happening at plate boundaries. And we'll see that all the amazing geology that we see on our beautiful planet, how plate tectonics has lent itself towards these processes. And then finally, we'll go on to discuss the importance of plate tectonics to Earth, life, and prebiotic life conditions. This will sort of be an introduction for you for next week's talk with Dr. Michael Casey, where you will actually talk more about evolution of life. But I'll just sort of introduce those prebiotic conditions and what role did plate tectonics play in that. And then finally, we'll look at plate tectonics on other worlds and what evidence we have seen so far with our various missions and what missions are coming up, which will probably explore plate tectonics on other planets. So to start with, some of the terms that you may have heard yesterday, we are looking at, let me just activate my laser pointer here so that, okay, so this image right here, okay, can someone confirm that my laser pointer is visible to everyone? The red dot?
Yes,
Okay,
it is.
so we are looking at a cross section of our planet, and you can see two sides to it: compositional layers and mechanical layers. And you learned how when the planetsimals came together and coalesced together to form these protoplanets that eventually grew into Earth. We had this process of differentiation based on the elements that were coming together, and the densest materials sunk down to the center of the planet, forming the core. The less dense ones formed the mantle, and the least dense ones formed the outer crust. So when we are trying to imagine our planet, try and think of a boiled egg, how it has those three distinct layers. You have the yolk of the egg, which is the thickest, and then you have the white of the egg, which is the next thickest layer, and then finally you have the shell of the egg, which you have to take off. Usually you have to take it off before you eat it. So that's like the crust of our planet. So when we are talking about a planet in terms of compositional layers, what are these rocks made up of and what are the elements contained in them, then yes, we divide it up into three distinct layers: the core, the mantle, and the crust. The densest being the core and the thickest layer. The next dense and the next thickest is the mantle, containing mostly of magnesium and some iron elements. Core is mostly iron and nickel, so that's why it's densest. And then finally the crust, which is mostly rich in silicates. Now, when we say that the crust is rich in silicates, that does not mean we don't find any iron in there, because you would be like, hey, why do we find all those iron ore and everything in the crust then if all the iron is deep inside the core? Well, it's a little more complex than that. When I say that the Earth is divided up into its three main compositional layers based on relative densities, we are really referring to the abundance, the relative abundance of these elements. So yes, the most amount of iron sunk into the core, but we still have some iron on our crust. So that's why you find all that iron ore and iron-rich rocks. And when we are looking at the crust, you'll notice that the crust is actually divided into the continental crust and the oceanic crust. Now, this difference in the crust thickness was very interesting to us. It's very interesting because you see this difference in the thicknesses of the crust and also the composition of what the crustal rocks are made up of. So I said, yes, crust is mostly made up of silicate-rich rocks, but when we get deeper into studying these rocks, you'll notice that the oceanic crust is more rich in basaltic rocks, the iron-rich rocks. And then it's also thinner. The oceanic crust overall is much more thinner and much more denser than the continental crust, which is much more thicker. And also it's less dense because it's mostly made up of silicates or granitic rocks. And I'm talking about the overall composition here. The continental crust, of course, it's thickest wherever we have mountain ranges. Now, that's just a brief overview of what you learned about yesterday, what happened and how the planet differentiated, and you formed these three main layers, and then formation of the magnetic field because of the because of the outer core and the rotating motion of all of that iron core that's in there. When we start thinking about and when we start talking about plate tectonics, we talk about the planet more in terms of its mechanical layers. So we are looking at the right side of this diagram right here. And you'll see that the mechanical layers, that's where we further subdivide the layers, the compositional layers, based on what are the mechanics, what are the conditions, what are the dynamics of the rocks that are in there. And this is a more complicated way in which geophysicists like to explain what's happening inside of our planet and outside of our planet in terms of plate tectonics. So you'll see that the core is divided into two distinct layers: the inner core, which is the solid layer of the core, and the outer core, which is liquid. And this is the reason why we have the magnetic field. The revolving motion of the liquid outer core is what causes the magnetic field to be surrounding our planet and protects us from all those harmful radiations from space. As we go out into the mantle, so this is the lower part of the mantle. Sometimes it's referred to as the mesosphere, but oftentimes I just tell my students that just call it the lower mantle, because we also have an atmospheric layer above our planet, which is also called the mesosphere. So just so that we don't confuse ourselves, let's just call it the lower mantle. And then as we reach towards the outer part of the mantle, this layer, this is a very interesting layer, and you may want to remember or write this name down somewhere, the asthenosphere. This layer, if we look at this the diagram at the bottom, which is just showing you the two upper layers of our planet, the two upper mechanical layers of our planet, the asthenosphere is the weak ductile layer. This is where you have molten rock, or something that we call magma. This is where magma is, which is basically molten rock material. And this is a ductile layer which basically flows. When I say flow, think about it in terms of not water. Water flow is much faster on the surface, but think of it as a layer, something that is molten rock, which is flowing at a slow pace. And then we have the outermost mechanical layer, which is comprising of the crust and the upper part of the mantle, which forms the lithosphere. And we are basically all living on the lithosphere. So lithosphere is what is the outermost layer, or the outermost mechanical layer of our planet. Now, if it's a specific question, and we will not ask you this question, okay, unless you were in a geology class, it's only then when we ask these questions to confuse students. What's the outermost compositional layer? And someone will write, it's lithosphere, but that's wrong. The outermost compositional layer is the crust. But when we ask, okay, what's the outermost mechanical layer? Then yes, the answer is lithosphere. But this is just something for those of you who are geology enthusiasts out there and plan to take geology classes later on in life. Just know that the outermost mechanical layer is the lithosphere, and then the layer that sits beneath it is the asthenosphere. And these are the two layers that we will be concerning with ourselves today, in terms of thinking about plate tectonics and how plate tectonics works. Okay, so that's a picture showing you, this is where the molten magma is. So that color reddish orange that you're seeing, that's representing molten magma. And then you have the outermost lithosphere where we sit. So lithosphere comprises of the oceanic crust, which is the ocean floor, and then the continental crust, which is all our continents where we live, where you have valleys and mountains and trees and animals and plants and everything else. So that's our continental crust. But both of that is basically the lithosphere. So lithosphere comprises of both oceanic crust and the continental crust. Now, plate tectonics tells us, or what we have learned from plate tectonics, is that lithosphere is not this rigid layer like the shell of an egg. It's not a continuous layer. It's broken up into these various plates, at least 15 different plates that fit together like a jigsaw puzzle. So imagine, and I ask my students to imagine a lot, because in earth science, you have to use that, especially because I'm teaching without any diagrams, without any capability to draw and show things to you, or any videos, which are really necessary for learning about earth science. But then I'll just ask you to use the power of your imagination. Think of a globe. I'm assuming everyone's seen a globe at some point. So if you take a globe and then just cut it open and lay it flat on a table, then that's what a globe would look like. So the lithosphere is the outermost layer, and it's not a rigid layer. It's broken up into these different plates, which are known as lithospheric plates. And that's what plate tectonics basically tells us, that our planet is not a rigid outer layer. It's broken up into different lithospheric plates. And these plates are actually not well-behaved students in a classroom who are super enthusiastic about astrobiology and are not moving at all. These plates are actually moving. They're constantly moving. There's always something going on. But these movements are really tiny, or the rate is extremely small. They are moving at a pace of a few millimeters to a few centimeters every year. The highest rate that has been discovered is actually along the Nazca Plate, and that's moving at a pace of 10 centimeters per year, which is the fastest rate. But everywhere else, the plates are moving at a rate of about anything between 1 to 2 centimeters per year, which is, again, it's a very slow pace, but just know that these plates are always moving. There's always some kind of motion going on. And we'll discuss more about that in the following slides. And we'll see what happens when these plates are moving and what causes that movement to take place, and how does that affect us. So when you hear that anecdotal phrase that the ground moves beneath us, it's actually very true. And I wonder if the person who coined that phrase knew about plate tectonics, because that's where that phrase comes from. Yes, the ground is always moving beneath us, except that it's so slow that we never feel it. Unless there's a major earthquake, or you live in California, then you feel it every other day, or in any area that is very prone to earthquakes. So before we go into all of that and what's happening between these plates and what do they do and how do they do it, let's talk a little bit about the history of plate tectonics. So this is a slide from yesterday that John already showed to all of you. I just wanted to bring it up again today just to reinforce that message that we want to pass on to you, that our planet's face has changed over geologic time. And the figure that you're seeing here, it's actually mapped out only from the last 650 million years to about 250 million years into the future. So this is not the entire snapshot of our planet's history. Our planet is 4.54 billion years old. So yes, the planet looked very different 4 billion years ago, when just very small continents did not really exist. They were just really small islands floating around. So this picture is just showing you what the planet looked like 650 million years ago, and then how plate tectonics has changed over time. And then approximately at this time, between 306 to 255 million years ago, is when we had that supercontinent called Pangaea. We'll be discussing about that in a little bit, and how the history of Pangaea came to be, and how geologists piece these puzzle of our planet's movement together. So, and then this simulation has actually gone on to show what will happen into the future. So this is our modern world. This is what our world map looks like right now with the 7 continents. But then if you go 50 million years into the future, you can see that Africa has moved a little bit upwards and joined more towards the western side of Europe. North America and South America seem to be moving and coming together on this side to eventually converge with Eurasia, or Afro-Eurasia, I should call that giant supercontinent forming there. If we go 150 million years into the future, again, that plate tectonic movement is bringing continents together, and then eventually 250 million years from today, that's what our planet would look like. And I noticed a question someone asked yesterday, which was very interesting and a good question, that how were geologists even able to figure this out? What will this look like in the future? So this is from Studying Geology Today. There's something called in geology. There's a theory that we say that the present is key to the past, but then it helps us. We look at the processes in geology that are happening today, and it helps us piece the puzzles of what happened in the past, because the geologic processes are happening the exact same way. So just because we can calculate these, just because we can calculate the plate motions, and just because we know the direction in which these plates are moving, that's how we are able to piece together computational models of what the future of our planet would look like. So if we figured out a way to live forever in distant galaxies and then visit our planet sometime in the future, 250 million years from today, that's what we'll see. How did this all come together? So I really wanted to talk about this story of plate tectonics, of how it came to be, just because I find it fascinating, and it's definitely it's a good story to learn about. And if you already know about it, then you'll just have to sit and listen to me once all over again. But for those of you who don't know the story, the concept of plate tectonics has been known. People knew something was going on. But Alfred Wegener, around 1915, that's his photograph on the left-hand side, he was a naturalist. and he fought in the First World War. He was injured and he was lying in the hospital, going through books of geology and ecology and biology just to pass his time. And he was looking at all these evidences of how there were patterns. He noticed certain patterns. One, that all the continents that he saw in the modern world map, they sort of fit together in his mind like a jigsaw puzzle. So say the east coast of North America sort of fit really well with the west coast of Europe, and then parts of the west side of Africa, and then the west coast of Africa fit really well together with the east coast of South America. So he started noticing these patterns, and then in the ecology books or biology books, he noticed that there was a pattern in which different animals, flora and fauna were found on different continents. There were certain latitudes where you found similar plants and animals, and then similar fossils had been discovered along these latitude chains. So he started to put these puzzle pieces together, and there were other evidences which he saw that not only flora and fauna, but even geological features. So say we know by this time, geologists knew about ancient ice ages before humans came into the picture. There were ice ages and mass extinctions. And we know that when ice moves through the ground, or when glaciers basically move through the ground, they form these glacial grooves because glaciers have a lot of power to erode material. So as opposed to say a flowing river, which erodes material every day, that's at a much slower pace. But then glaciers, because they are made of their ice, they have much more power to erode large chunks of material. So when you look at glacial grooves on the ground, they are much deeper than what you will see that may have been caused from, say, a river erosion. A valley that has been formed from river looks very different from valleys that have been caused because of glacial erosion. So Alfred Wegener was looking at all these maps that existed of land masses that had these glacial grooves and glacial erosion, and they sort of followed this pattern. He's found that similar grooves existed in parts of Australia that matched with Antarctica, and that matched with parts of India and Africa and South America. So he started to piece these things together, and he coined the term continental drift. And he proposed that at some point in time in our ancient history, he basically projected 300 million years ago, there was a supercontinent on our planet, and he called it Pangaea, where all the continents in the world today, the 7 different continents, were actually connected. That was one landmass. And they have now separated. They have moved away. So this was his hypothesis of continental drift. It was not accepted. It was actually laughed at by geologists. And the reason was because he had no way of explaining that mechanism. So he said, okay, continents were connected, and because he's noticing these patterns, and it seems like it was one giant landmass, and now they have separated, but he had no way, or no valid scientific way, I should say, to explain how these continents had even moved away. So it was laughed at, and that hypothesis was discarded until later on, around 1928, when a team of geologists in New York revisited this to study some of the ocean geology that they were looking at, and they tried to use that continental drift hypothesis again to explain some of the things, magnetic anomalies that we look at, why that magnetic anomaly happens, the magnetic switching of poles of our planet happens because of plate tectonics. They tried to use that again, but then they again did not have any way of explaining how these continents had moved away from each other. So this theory was not revisited again until the 1960s, and we'll see why. So of course, Alfred Wegener again had other gaps in his hypothesis. He also incorrectly believed that only continents were moving. So he just thought that he called it continental drift because what he assumed was only the continents were moving. At that time, he was not thinking about the ocean floor at all. He wasn't thinking about any movement of the oceanic crust at all. Of course, now with our modern technology and with knowing about plate tectonics, we know that it's not just the continents, but it's the entire lithospheric plate that moves. And lithospheric plates actually have both the continental crust and the oceanic crust. So if you're paying attention to this little diagram here, this is again the same diagram we saw a couple of slides ago of the various lithospheric plates. And if you can see these lighter colors, it's basically marking out the land masses, the different continents that we have. And then the other parts where my laser pointer is right now, that's where the Atlantic Ocean is. So where my laser pointer is sitting, it's the oceanic crust or the ocean floor of the Atlantic Ocean. So there is still lithospheric, it's still part of a lithospheric plate. This entire plate is known as the North American plate, or say this entire plate is called the Eurasian plate, where you have Europe sitting on it, and then parts of Asia sitting on it, on the Eurasian plate. So now we know that lithospheric plates are not just continents, but it comprises of both the continental crust and the oceanic crust together. But this is something we know now. This is not something Alfred Wegener knew back then. So what happened in the 1960s? What was so special? This is when a lot of extensive mapping of the oceans was being done. This is after World War II, and the ocean mapping was being done mostly by the labs that served the military to detect submarines, to detect enemy submarines, and to basically for national security purposes. That's when they started to map the ocean floor extensively. And the same lab in New York actually created a map where they saw that there was this center ridge in the mid-Atlantic Ocean, which was very susceptible to earthquakes. And it had a deep crack-like valley formation. There was also volcanism going on. Parts of it also has volcanoes. For example, Iceland has active volcanoes. It actually sits very close to this entire central deep ocean ridge. And I'll give you the name of this ridge. It's called the Mid-Atlantic Ridge, and it's actually a plate boundary. It's a specific type of plate boundary. It's known as a divergent boundary. So this lab, when they discovered it, and this happened after they had mapped the ocean for what was happening on the ocean floor, that's when they really discovered a mechanism to explain Alfred Wegener's continental drift. Because let me just go back one slide. Alfred Wegener said that, okay, 2 slides. Alfred Wegener said that, okay, this was all one giant landmass, as Pangea, which now we know is true, and they had drifted away. It would make sense that they moved away, because if there is a plate boundary that, if you follow my laser pointer, if there's a plate boundary, that's a divergent boundary, which means that this is where the plates are being pushed away from each other and new ocean floor is being created. Then moving on to this map right here. So this boundary line, if you look at this boundary line, that's the Mid-Atlantic Ridge. This is the divergent boundary that caused new ocean floor to form. It caused these 2 lithospheric plates to move away from each other. So not just to actually force, so North American plate and Eurasian plate moving away from each other. And then in the Southern hemisphere, we have the South American plate and the African plate that moved away from each other. So it's actually the longest divergent boundary on the surface of our planet. It runs from the Northern hemisphere all the way to the bottom of the Southern hemisphere. And this is what caused this giant landmass that was once compacted together as Pangea to gradually move away, to gradually separate out. And then other divergent boundaries, of course, around the planets caused other continents to just move away from each other. And eventually what our world looks like is sitting with 7 continents. But yes, the first one that they discovered and they could actually explain that continental drift was with the Mid-Atlantic Ridge, after they had mapped the oceans for a whole different purpose. So there was something good coming out of all this research that was done for the military. They were finally able to explain plate tectonics. Another very interesting thing that lent itself towards developing of the plate tectonics theory, not a hypothesis, but a theory that now scientists accept it widely, and this is the means of how we explain everything on a planet, was geologists in the past had noticed that the rocks that form in the ocean floor because they are rich in iron, the alignment of that with the poles, the magnetic poles of a planet, it actually switches over geologic time. But there was no way to explain why this switch is happening until they really discovered the mechanism of plate tectonics. And now, of course, the most recent papers of geophysicists who study this phenomena are actually trying to calculate how frequently does magnetic poles switch. For example, right now, our magnetic north pole is aligned with the geographic north pole of our planet. But in geologic time, this will change. The magnetic north pole, the compass on your iPhone or smartphone, the magnetic north will actually point towards Antarctica. If I don't know if it'll happen in our lifetime, we don't have any evidence for that, but I'm just saying, say somehow we find a way to live forever. And then if you're still using smartphones and you're using a compass to align the magnetic pole, then the magnetic north will be aligned with the geographic south. And this has happened several times in our geologic history in the past. So this has been recorded in the oceanic crustal rocks, but until the discovery of plate tectonics, scientists really weren't able to explain what causes this phenomenon. And now, of course, they're saying that the further the continental crust or the continental mass moves away from the equator, the further the center of gravity is, the more frequently the magnetic poles shift. So say it can go up, it can switch up to 6 to 8 times in a span of 1,000,000 years. So that's a lot of switching of magnetic poles if we are talking in terms of the geologic time. Of course, 1,000,000 years is a lot for humans, but it's really not that a lot if we think about the age of our planet, because that's 4.5 billion years that we are talking. So again, this was another evidence that helped geologists actually make sense of what was going on our planet. So, excuse me, I'm just going to take a sip of my tea. Sorry about that. I just start to lose my voice because I get excited about plate tectonics and start to talk really fast, and then I lose my voice. So want to hold on to that for a few more slides. So talking about what powers plate tectonics, and this is to really understand this, I have a picture of something called lava lamps. And again, I'm assuming most of you have seen these. And if you have them at home, maybe turn it on tonight or later in the day and try and think of the process of what's taking place on our planet. So I have these pictures side by side. Again, we have a cross section of our planet showing you the lithosphere or the Earth's crust, and then what's happening in the mantle or the asthenosphere where the molten magma is. So let's talk about lava lamp first. This is what happens in a lava lamp. Or at least this is what my understanding is what's happening in a lava lamp. When you turn on the lava lamp, there's a light bulb at the bottom, which basically heats up this wax that's in there. So initially all of this wax is clumped together more like this. Everything is at the bottom. Lava lamp has been turned off for 8 hours, so everything's just clumped at the bottom. When you turn on that light, it takes a while, and the light bulb actually heats up that wax. As it heats up, it becomes less dense than the liquid that's there in the lava lamp. And because anything that's less dense will always float at the top. And differences in densities, if you have seen, if you try to pour oil on water, you will notice that water, what floats, okay, yeah, I cannot communicate with people here. So oil always floats on top of water because oil is less dense, okay? So anything that becomes less dense will always float to the top. So this wax actually heats up, it becomes less dense, and it goes to the top and clumps around here. So you have all these globules of the wax clumped together. It looks really pretty, but it's just because it's less dense. And now once it's at the top, there is no light source here. There's no heat source at the top. So all of that wax actually cools down and becomes more dense now. And once the density increases, all that globule basically sinks down to the bottom again and meets this wax clump that's lying at the bottom right here, which is still heating up. So this process, or this cyclic process, is very similar to the Earth's convection cycle. So heating up the source, material becoming less dense, goes to the top, that's where it accumulates, cools down eventually, gradually becomes more dense and sinks back to the bottom. The same process is what's taking place in Earth between the asthenosphere or between the mantle and the lithosphere. So as rock is heated and it becomes less dense at divergent boundaries, when plates move away, there is a sort of melting or there's a sort of decompression that takes place. The less dense rock rises up from this ocean ridge and creates volcanoes or forms new ocean floor. Now, you may be wondering, is there a place on Earth where I can just go and stare down into the mantle? No, there's no ridge where you can actually go stare down into the mantle. The process actually takes place. It's a much thicker layer than what you're seeing in this picture, okay? So what really happens when you go and look down at this ridge, you will just see new rocks that have formed from the magma that has erupted. So magma basically rises up from the asthenosphere because it's less dense. It comes up through these ridges, cools down, forms new ocean floors, and then eventually and gradually, because these lithospheric plates are moving, these rocks become older and older. They are now cooled down and they become more and more dense because of accumulation of materials that takes place on the ocean floor. And as they become more dense, this picture is actually cutting off another boundary here, and I'll show it to you in one of my later slides. But there's a convergent boundary. That's where ocean floor actually subducts or sinks back down into the mantle. So this is really dense rock, or this is the really dense rock plate that is sinking back down into the mantle to melt again, just like the lava lamp, or just like the process that's taking place in the lava lamp. So you have these wax globules that lie at the top, they cool down and they become more dense and they sink back to the bottom. So you have magma rising up, it cools down, becomes the ocean floor, and then it goes to another plate boundary where the process of subduction is taking place, or sinking back into the mantle is taking place. If you don't remember subduction, it's okay, folks. Just remember sinking back down, and that's good enough for this workshop, okay? So, and this will help you remember things longer. So subduction you may not remember the term, but at least as long as you remember, this is what's taking place, sinking back down of more dense rock material back into the mantle. So this cyclic process, by the way, it's happening over millions of years. Okay, so we are talking about millions of years. This is not something that you can see immediately in your lifetime, but we can measure the movement of plates. Like I said, these plates are moving a few centimeters every year. That's something we can measure, but this is the process that's taking place. And this leads to very interesting geology that we'll talk about. So this is the power engine of plate tectonics. What's happening at plate boundaries? So I talked about two plate boundaries right there. So plate boundaries is where all the action is. Like I said, these plates are not sitting still, but there's always something going on. Either these plates are moving away from each other, so at divergent boundary, or they are coming together. We call that convergent boundary, or they're simply sliding past each other. So these are the regions that we call as plate boundaries. It's the boundary where two plates either come together, or they move away from each other, or they simply slide past each other. So think in terms of, if you're looking at this map right here, this is representing a plate boundary, or one of the largest areas where volcanism and earthquakes exist on our planet. It's known as the Pacific Ring of Fire. And these red dots are actually representing active volcanoes on our planet. So all along the Andes mountain range, you have active volcanism. And then as you move into Central America, coming all the way up to North America, here in Northern California, Oregon, Washington, going up to British Columbia, and then going all the way up to Alaska, and then coming all the way towards Asia, going down towards Australia and New Zealand. So this entire region is an active volcanic site. And that's because the Pacific plate, one of the largest tectonic plates, it's locked in a sort of convergent boundary at all its sides. And we learn wherever convergent boundaries exist, or wherever two plates come together, they actually create volcanism. If one of them is an oceanic crust and the other one is a continental crust, you will almost certainly have volcanism or active volcanoes and earthquakes. So both of these will will exist at these plate boundaries. So I just wanted to give you an idea that this is what's happening, but we'll discuss each of these plate boundaries one by one with individual slides dedicated to them. So let's, just before I move on to the boundary once again, I found this another diagram, which I thought would explain the process by looking at the cross section once again. So I put it here. So let me just talk about it a little. So going back to this image, which I was talking about, and I said, okay, this is where magma rises because it's become less dense. Now we are looking at this same diagram. This is what's happening, the Earth's convection cycle. So you have a plate boundary where two plates are moving away from each other. So less dense magma rises at a ridge, creates new ocean floor. And then you can see there's a convergent boundary. This is where the plate is sinking back into the mantle and again, liquefying again or becoming molten magma again. So solid rocks again becomes molten rock. So that's again, convection cycle, looking at it in a different diagram. I just put it there so that it makes more sense. Let's talk about boundaries and what happens and what geology do you see. And this will be helpful if, if you become an astronaut someday and you're sent to Mars or to another planet and you want to find out that if ever plate tectonics has happened on those planets, just in case we haven't already detected them, then how do you identify features? What do you look for? And it also helps you determine how to look for analog sites, which I know is something Dr. Siddharth Pandey will talk about later today. It's one of the activities for your class where you will be identifying analog sites. So some of the features that we look for at these plate boundaries. So just know that at active plate boundaries, you have volcanism and you have earthquakes taking place. At divergent boundaries, when you have two plates moving away from each other, you have a rift valley if it's a continental plate, or an ocean ridge if it's an oceanic plate. So think in terms of the mid-Atlantic Ocean or the mid-Atlantic ridge in the Atlantic Ocean. So that created the Atlantic Ocean because of the formation of the oceanic plates that sit beneath the water. So that was a divergent boundary. Now, if you have a divergent boundary in the sitting beneath a continent, that will just create a rift valley. It will cause an entire continent to split apart into two. This is something that is there in Africa. I saw a question yesterday, so I just want to revisit that question. Somebody asked that, will Africa eventually split into two? Yes, the answer is yes, because of the divergent boundary that's sitting beneath Africa. It's more towards the eastern side of the African continent, and that's created the rift valley. Gradually, what will happen is that the two land masses will move away from each other, but that doesn't mean that there will be a gaping hole into the mantle where people can just go and look at what's happening inside the mantle. It will basically just, the magma will just rise from the mantle and create a new ocean floor. So a new ocean will form. It will start off as a small sea-like formation, and then gradually, yes, because plate tectonics happens over millions of years, gradually it will become a larger ocean. So as new ocean floor forms, nearby water bodies, basically water from the nearing ocean rushes in to basically equilibrate and fill up that valley and create that new sea-like formation or ocean. So this is how oceans are created. So it starts with a rift valley if it's sitting beneath a continent. If it's already sitting, if the divergent boundary is already sitting on the ocean floor, then you basically see deep ocean ridges. You will sometimes find volcanic features here, and always, always earthquakes. So divergent boundaries will always have these earthquakes. One other feature, I'm not sure if it's in my next slide. Okay, it's in one of the later slides. I'll come back to it. It's a feature that you often find near divergent boundaries and hydrothermal vents. I'll talk more about that in coming to a later slide when I have the picture of hydrothermal vents. They are very interesting for those studying or those interested in studying the origins of life. And I'll come to that a little bit later after we've talked about the other boundaries. So this is the divergent boundaries. Know that the name divergent means diverging away. So this is where lithospheric plates are moving away from each other. It's like you had a fight with your friend and you're just walking away from each other. All right. Convergent boundary, it's coming together. You made up with your friend and you want to give them a hug now. So convergent boundaries is where you have plates coming together or coming towards each other. Now, when plates come together, there's a lot of action. There's a lot that goes on. That's where volcanoes are created, and this is how orogeny or mountain building takes place. So I have three examples here. We have two different types of plates, right? We have we have the lithospheric plate, but then I said it has two different types of crust. We have the oceanic crust and we have the continental crust. And before I started, I mentioned something about the oceanic crust being more dense and the continental crust being less dense. So remember this key concept because it will help you understand what's happening at convergent boundaries. So oceanic plate being more dense. So I said that whatever is more dense, it goes to the bottom, and whatever is less dense sits on top. So when two plates come together or when two crusts come together, if one is the oceanic crust being more dense will sink back into the mantle, and the continental crust will sort of ride on top. It will lead to the formation of volcanoes. And if there's any accretion of landmass taking place, it will also lead to the formation of mountain ranges. But this is where you will also find trenches in the ocean floor. So this is one example of the Nazca plate, which is the lithosphere, which is the name of the lithosphere right here. And Nazca plate is actually an oceanic crust because you have the South Pacific Ocean here. So Nazca plate is coming together or converging with the South American plate, which is the continental crust. And Nazca plate is actually sinking very slowly into the mantle and melting there. So this has led to the formation of volcanoes along the Andes mountain ranges. Here's another example. You have two oceanic crusts coming together. So when you have two oceanic crusts, Eurasian plate actually consists both of the continental and oceanic crust, but this is the oceanic crust part of the Eurasian plate coming together with the Pacific plate. So when two oceanic crusts come together, because both of them are dense plates, the older plate will have more density because of the build-up of material on the ocean floor over geologic time. So in case of Eurasian plate and Pacific plate being the older one is the more dense plate, and therefore that is the one that's sinking into the mantle right here. And that has led to the formation of volcanoes along Japan. And that's where you have the trench. So this is another type of convergent boundary where you have two oceanic crusts coming together. Finally, we have what we call a continental collision, or when we have two continental crusts coming together. Now, both have same densities. Continental crusts have lesser density than oceanic crust. Now, we know that when oceanic crust comes together or collides with a continental crust, the oceanic will sink back down. But when you have two plates coming together that are both continental crust, then there is no sinking into the mantle taking place. There is actually uplift and accretion and pushing up, or orogeny, that is known as mountain building event takes place. So this is what led to the formation of the Himalayas. And I have a better image, I think, in my next slide. Yeah, so this is what happened. The Indian landmass, which basically broke off from the Indian Australian plate because yeah, and at this time, obviously humans were not around. So we are talking about millions of years ago. We still had dinosaurs at that time. So that plate started to move upwards towards the Eurasian plate. And you can see that path it has followed. So the landmass is a part of the continental crust. So when this slams with the continental part of the Eurasian plate, there was upliftment and there was accretion of the continental landmass, which led to the formation of the boundary that we have here, which formed the Himalayan mountain range. All right, so this process is known as orogeny. Again, not important for the sake of this workshop. It's just something for people who are interested in geology. Orogeny is a mountain building event. This is basically how most of the mountain ranges around the world have formed. It's when two continental crusts have collided with each other at some point in our geologic history that has led to the upliftment of these continental crusts and formation of mountain ranges. Now, more recent research, and this is just a fun factoid, University of Chicago researchers a couple of years ago, they actually went to the Himalayas to do a deep study of the rock mass and rock volume. And they found that the amount of rocks that is, or the volume of rocks that should have formed the Himalayas, actually some of that content is missing. And they determined that it may have been, let me go back to the previous image just so that it, or maybe in the same image. It may have been that India was actually sitting on a plate that also had an oceanic crust. So when that crust collided, it actually sunk into the mantle. So there was some event of subduction. And that actually caused some of that continental crust to also subduct or sink into the mantle along with the oceanic crust. And then, of course, the rest of the landmass basically just collided, and there was more upliftment of the landmass and formation of the Himalayas. So this is why the Himalayan region, it's highly faulted. You will not see any volcano formation here because there is no active sinking of any oceanic crust taking place. So there's no melting happening. And I'll talk about what melting and what really creates volcanoes a little bit later on. But just know that the Himalayan mountain ranges, it does not have any volcanoes, but there is hydrothermal activities. It's a very highly faulted zone. So Nepal has earthquakes almost on a daily basis because it lies on a very, very highly faulted zone. So you do see very interesting geology here and some analog sites that I will not give away. I will not give away any names, but just know that it's a highly faulted zone. It's interesting. It has hot springs, and that's all happened as a result of this continental collision that has taken place and the highly active plate boundary that it sits on. All right, so that's what's important and that's what's interesting to know about. So how do volcanoes form? Before I go on to the third type of boundary, I wanted to talk about how volcanoes are forming at divergent and convergent boundaries, only because the third boundary does not have any volcanism associated with it. So volcanism happens because of the magma becoming less dense, because of melting, and two types of melting. So at convergent boundary, where you can see this oceanic plate going under. So as it goes under the continental crust, all of these rocks that's part of the oceanic crust, they melt because of the high heat in the mantle. And because they have they contain some water, it's part of the oceanic crust. So because the rock fissures, the rock does have some water content. So that basically lowers the melting point and it melts much more faster. So because it melts, it will become less dense and it will want to rise back again to the surface. And it does rise back again. It does eventually come off as volcanoes. So that's what creates volcanism, and that's what creates volcanoes near convergent boundaries. So wherever you have two plates coming together, and if there's a subduction going on, subduction meaning one plate is sinking into the mantle, you will have volcanic creation. And this is why I said at Himalayas, you do not have any volcanoes taking place because there's no active subduction happening right now. It's just two continental land masses that have collided and they have just uplifted to form those mountain ranges. So no volcanoes. But otherwise, if we talk about the Andes mountain range, or if you talk about, say, the west coast of North America, so all the volcanoes that we have in Washington State, in Oregon, or starting from British Columbia, Canada, coming down to Washington State, Oregon, and Northern California, all of these volcanoes have formed as a result of similar subduction events. And then at divergent boundaries, we have a different kind of melting taking place of rocks. So because of these two plates moving away, there's decompression that takes place over the magma that sits in the asthenosphere. And that decompression causes that magma to melt more and rise up really fast because it's becoming less dense. It wants to go to the surface. It rises and forms new ocean floor, or it comes up through volcanoes. So those are the two places where you will find active volcanoes being created. There is another place, but I won't give the spoilers right now. We'll come to that in a later slide with pictures and I'll explain that. But otherwise, on our planet, we find volcanoes wherever we have these two types of plate boundaries, divergent boundaries and convergent boundaries. All right. I'm hoping everyone is still awake and still with me. We can talk about the transform boundary, the third type of boundary, where nothing very dramatic is happening, unless, of course, earthquakes, major earthquakes. Yeah, I shouldn't say nothing very dramatic, because California does have many, many earthquakes, and some of them are more dramatic than the others. So at transform boundaries, this is what takes place. Plates simply slide past each other. So think about it this way. Say if there's a very crowded hallway, you're going to classroom, and COVID is over. So yeah, we're not having social distancing anymore. And it's a crowded hallway where you're walking towards your class and you bump into some people. Say you bumped into another person. Now that bumping action, or just that brushing past that other person, will cause both of you to shake up a little bit. Now try and put that, extrapolate that to, and apply that to plates on our planet. When lithospheric plates, when they slide past each other, that shakes up the ground. So that's what causes earthquakes at transform boundaries. So transform boundaries, there's no volcanism happening because there's no melting taking place. There's no flux melting. There's no subduction. There's no sinking of plates under into the mantle, or there's no plates moving away, causing that gap to form and cause magma to rise up. It's just plates simply sliding past each other and creating earthquakes. So that's what's happening right along the San Andreas fault zone. So the faulted zone is basically the deep fissure. And along this faulted zone, the North American plate, you can see the relative motion is slightly downwards. And then the Pacific plate is moving upwards. So that they're going in opposite directions. So they have that brushing past each other motion. And that's what causes frequent earthquakes in California almost every day. Most of these earthquakes are very small on a Richter scale. Like I get alerts on my phone for earthquakes, anything between 2.3 to 2.5. I don't really feel them. The last earthquake that I felt was on the day the Mars Perseverance launched. So July 30th, that's when Pasadena had a major earthquake, but it wasn't major. It was just on a scale, I think it was 4.3, and we felt those tremors here. But otherwise, we have earthquakes every other day on a very small scale, which is a good thing. Although geologists do anticipate a big earthquake happening sometime soon because of the forces or because of the tension that's been building up for some time. Otherwise, just know that transform boundaries is where you find faulted zones and you just have earthquakes taking place. I put this fun fact in here. So these plates are moving at approximately 5.5 centimeters per year, which means that at this rate, if I stay alive for that long, I live in LA right now. So in about 9 to 10 million years, I'll be sitting next to San Francisco, which is in Northern California right here. So because this plate will eventually break off, and Los Angeles, this will eventually break off and move upwards and reach towards San Francisco, but in 9 to 10 million years. I'm hoping if I'm alive, I'm in some distant galaxy, not in LA at that time. All right. So volcanoes, coming back to volcanoes, this is the spoiler that I didn't want to give away. And this is interesting because you will find, if you're astronauts and if you go look for tectonics on other planets, you will find volcanoes. And even now, when we are looking at volcanoes on other planets, not all of them are because of divergent or convergent boundaries. So this is where hotspots and mantle plumes come in. So this is something that's existed on our planets ever since it cooled down. We have these plumes of hot magma that basically rises up from mantle towards the lithosphere. And it's so hot and intense that it basically pushes up and burns holes through the lithosphere and creates volcanoes. So these are known as hotspots, all right? And enough research is being done to understand more about the nature of where and how these hotspots form, but we do not know enough yet about the nature of which location these are going to exist in. So we can only study them if we see volcanism taking place, and if that volcanism is happening in an area where there's no active divergent boundary or a convergent boundary. And one example that I really talk about is Hawaii, the Hawaii chain of islands. It actually sits, if you can excuse me, I'd like to go back to a couple of slides. I just want to show you that plate picture again. So Pacific Ocean, you have this specific plate. Let me find a better picture. I'll go back a couple more slides. Sorry about this, folks. But yeah, so you see the Pacific plate, and Hawaii is sitting right here where my laser pointer is right now, okay? And Hawaii has active volcanoes, or an active volcano, but it's not close to any boundary. You can see that the boundaries are all the way far away. So Pacific plate, but it's in the center, almost in the center of the north part of the Pacific plate. So let me go back to hotspots. So this is when geologists discovered that we have these areas on our planet and on other planets in the solar system where you have these mantle plumes that create hotspots or that create volcanoes where magma just comes out, burns a hole, burns a volcano in the lithosphere. Now, a chain of islands have formed at Hawaii, and all of these are volcanic islands. So, if you're looking at this, you have the Maui, Oahu, and Kauai. These islands are basically extinct volcanic islands. The only active volcano is now in the Big Island, Hawaii, or Big Island of Hawaii. But all of these islands were ancient volcanoes. They are not active volcanoes anymore, and this is why. So, mantle plumes are basically just magma coming out of the mantle and coming out into the lithosphere and creating that volcano, right? But we have something called the lithosphere, which has a mind of its own, and it doesn't sit in one place. We know that it moves. So because the lithosphere, or because the Pacific plate is moving, it has caused these volcanic islands that were created many, many millions of years ago. For example, Kauai is almost 80 million years ago, or 87 million years ago, and then Oahu is 77 million years ago, and Maui maybe 65 million years of maybe 50 million years old. So these used to be volcanoes when they were sitting right above this hotspot. But because the lithospheric plate has moved away at its very slow pace of a few centimeters every year, these are now extinct volcanic islands that form the Hawaiian chain of islands. And the only active volcano is actually in the main Big Island of Hawaii. That's because the island sits above the hotspot. So hotspots can form either in the ocean floor or they can form in the continental crust. And we'll take a look at some more examples on our Earth. But these are interesting to study because this is another way in which volcanoes form on our planet. And this is another way to explain when we find volcanoes on other planets, and there may not be any plate tectonics or plate boundaries going on. So some more examples. I wanted to, of course, my profile picture from Twitter is coming from a hotspot eruption. So this is in Idaho in US, where you have these volcanic lava flows that formed as a result of hotspot eruption. And because the plate moves, that hotspot is now actually under the Yellowstone National Park. So Yellowstone National Park is the major part of the park sits in a state called Wyoming in the US. It also has parts that's in adjacent states of Montana and Idaho. It's a really large national park, but the hotspot actually is sitting under the part of the park which sits in Wyoming. And this is the reason why Yellowstone is considered as a super volcano and has a whole bunch of hot springs and other geysers and mud volcanoes and very fascinating volcanic features that people can go study astrobiology in, or geology or microbiology in, with its extremophilic life that you find in the hot springs, and then other very interesting geological events that are taking place. And then some of the sites are considered to be analog sites for planets that may have similar extremophilic bacteria or hot springs or geysers. So it's this fascinating place. And then, of course, the very, very beautiful place called the Deccan Traps in India formed as a result of hotspot eruption. So I wanted to use this example more in the interest that there's interesting history or geologic history associated with it, besides the fact that a lot of Indian movies actually shoot their dance and song sequences at these locations because they're really beautiful. Deccan Traps lava flows, but also these are the lava flows that are responsible for the extinction of dinosaurs. So the KT extinction happened because of two reasons. It wasn't just the asteroid impact, but it was also the Deccan Trap lava flow that was taking place as a result of a hotspot eruption almost 65 million years ago. which led to the formation of these large lava flows. So it was happening over several million years. And whenever we have volcanic eruptions, we also have toxic gases that are being released in the atmosphere. So the atmosphere was already becoming toxic for most of the animals, the largest animals being dinosaurs at that time. And then, of course, to put the cherry on top, I shouldn't put it that way, but I mean, if dinosaurs were around, then we wouldn't be here. So I can use the term. The asteroid just came and impacted our planet and then made the environment way more hostile, which led to the extinction of the largest animals that were on Earth at that time, which are the dinosaurs, and basically paved the path for mammals to adapt and evolve from there. So the reason mammals survived is because the only mammals that were around at that time were rodent-like mammals or burrowing mammals, which could actually burrow into the ground and stay safe until conditions were safe again in the outside atmosphere. So they were kind of in a lockdown like we are right now because of COVID, but it wasn't for a short time. So COVID, of course, lockdown will get over in a few months, but these burrowing mammals were in a lockdown for a much more longer time. So I think we should all thank them for surviving that long lockdown because we were able to evolve, or humans were able to evolve from there. If those mammals had not survived, then most likely we would not be here. So those lava flows, of course, again, comes from hotspot eruptions that took place many, many millions of years ago. Finally, coming to the importance of plate tectonics. So we looked at features. We know that the most dramatic features on our planet have formed because of plate tectonic motions or because of the movement of plates. Whenever they move, they form mountains, they form volcanoes, valleys, and every other fascinating geology that we see on our planet. Of course, surface processes do also lead to the formation of these waterfalls and valleys and other things that form, but most of the most dramatic geology on our planet has formed and changed over geologic time because of plate tectonics. But how is it important to life on Earth? So if this cycle, carbonate and silicate cycle, or the geochemical cycle, or it's also known as the inorganic carbon cycle, this has been in place for the entire of Earth's history. If this cycle was not in place, then maybe Earth may have been a very hostile planet for life to, or complex life to not have evolved. And here's why I think that's would have been. So this is what the cycle is, and the cycle is still, of course, active today. Excuse me. So whenever we have carbon dioxide we have carbon dioxide in the atmosphere, but yes, carbon dioxide is also released from the volcanoes. So it exists in the atmosphere. It mixes with water when it comes down with rain, and it forms carbonic acid. It's a weak acid. So but it actually does, over long periods of time, it causes weathering of rocks, which are silicate rocks, also carbonic rocks. So that weathering, or that breaking apart of rocks, or that slow weathering of rocks, that material eventually actually flows down into rivers and then reaches the ocean, where it sinks, and that bicarbonate ions, or the calcium ions that's being precipitated from this weathering event, it's utilized by the marine life in the oceans, and that's what they use it to make their exoskeletons. So next week, when you learn about the evolution of life and evolution of complex life, you will learn how life evolved as a single cellular organism, and then the first types of eukaryotic organisms or complex life that we were forming, they were soft-bodied and gel-bodied organisms or marine organisms that did not have an endoskeleton or shell. And eventually it was because of this process, the carbonate silicate cycle, that made those ions, or that made those materials available in the ocean, that these organisms were then able to adapt and form an exoskeleton. And that's when complexity of ocean life arose from there. So this is the calcium carbonate that's sinking eventually down into the ocean floor. Once these marine organisms die out, all of that calcium carbonate along with silicate sinks to the ocean floor. And what's happening in the ocean floor? You have plate tectonics going on. So say about every 200 million years, that oceanic crust is sinking back into the mantle and basically melting. And this is where carbon dioxide from the carbonate is getting separated again and erupting out of the volcano, coming back into the atmosphere. So this carbonate and silicate cycle has played an important role in sustaining life on Earth, because oftentimes when we think about, or oftentimes when ecologists think about how different types of lives adapted on Earth and what were the material they were utilizing in their environment, if the first organisms that evolved in the ocean were soft-bodied, if the ocean was way toxic and if there was no material provided to them, then maybe endoskeleton may not have evolved, and skeleton may not have evolved, and complexity in ocean life may not have evolved. Or say if this cycling of material wasn't taking place, then all of that rain runoff that basically precipitates materials or minerals into the ocean may make the ocean very, very toxic over time. And that would eventually end up killing all of marine life. Something that we see today, we have this carbon dioxide sink that has increased because of climate change and because of human activities, which is leading to the bleaching of exoskeletons of marine organisms. So that we are seeing that, but that's because we know that, okay, humans are doing that, so we can talk to people and we can make them aware and we can put policies in place that protects marine organisms. But just imagine if this natural cycle was not in place, then maybe Earth may not have been, or Earth's ocean may not have been a very healthy place for life to evolve and become more complex and eventually maybe move to land. So plate tectonics indeed has played a very important role, and this is a cycle that is happening at a slow pace, but it's still an important cycle, or the carbonate silicate cycle, to recycle that carbon dioxide from the atmosphere back into the mantle and back into the atmosphere through volcanoes. Some other events that are related to volcanism, and it may or may not be plate tectonics related. And I say that because, like I said, in some places you may have volcanoes, but it may be in the absence of plate tectonics. And plate tectonics, we do not we do not have an exact time stamp that when exactly did it start. We believe it started sometime in the Archean eon, that is almost 2.5 billion years ago. And the reason for that is because the first couple of billion, the first 1.5 to 2 billion years in our Earth's history, our Earth was still cooling down. It had not completely cooled down. So we cannot, we don't see that distinct, we do not have evidence for that distinct subduction of plates and then recycling in the mantle and then coming back up through volcanoes. We have been able to study some of the minerals in the oldest rocks that exist in the zircons, but we don't have a timestamp of when exactly plate tectonics started. Maybe it started when the planet was formed, but we didn't have that exact mechanism of subduction and divergent boundaries because we didn't really have those many continental plates. We just had some islands floating around here and there. So this is why it's really important. Volcanism itself is very important for the spark of life that took place on our planet, but we don't know if plate tectonics played a role in creating that spark of life. We definitely associate volcanism with it. But plate tectonics, going back, I want to reiterate that, and I'll come back to this point, it definitely has sustained life on our planet for 4.5 billion years, or 4 billion years, however long life has been here. So a little bit about what feature we are looking at. On the left side, we are looking at a hydrothermal vent. So I said it's associated with volcanism, something you find near divergent boundaries, underwater volcanoes. And these are sources of where really superheated water actually precipitates a lot of interesting minerals and elements from deep oceanic crustal rocks and brings them back into the surface of the ocean with heated water. And some of these elements are really important to create interesting ecosystems around these hydrothermal vents. So a lot of scientists working towards origins of life also believe that life may have formed in near hydrothermal vent-like formations, or whatever we had similar to in the Hadean eon, the beginning of Earth, a tidal pool that was very close to active volcanoes, which may have had certain ingredients that basically sparked that first form of cell. our first living form. We do know that complex chemistry goes on around here, and volcanoes actually give off some very interesting elements that are vital for the formation of life. And you learn more about this in details next week, but some of the things, gases like carbon dioxide or water vapor, these are all given off with volcanism events, or carbonyl sulfate, sorry, carbonyl sulfate is kind of an ingredient that is important for amino acids to form peptides, which could have come from volcanoes. So these are all hypotheses that various scientists are testing. And again, you will discuss this later on in this workshop. But some of the first experiments that took place, and this is something this you may have seen this before, the Miller-Urey experiment, one of the very popular experiments. It was also the first experiment I was supposed to perform as a PhD student in my first month of starting my PhD. So you have you have a glass apparatus where you just basically take clean water. It's to simulate early Earth conditions, and you can you can put in gases like water vapor, methane, ammonia, and hydrogen, a mixture of these gases in the required ratio in this glass apparatus, and you put a heat source of water in there, and you simulate ancient lightning in the early Earth's atmosphere through an electric spark inside of this glass chamber. And I think we ran this experiment for about four and a half to 5 days. When you see that clear water start to turn murky brown, and eventually when you test that water, you have simple amino acids in there. So you can do a mass spec and find out what amino acids are forming. Now, this experiment was first performed in the 1950s, but since then it has been adapted in so many different forms by so many different labs around the world, for simulating different conditions on different planets. So say something on Titan, what gases do you find on Titan's atmosphere? Then scientists who want to study what kind of life form or what kind of complex chemistry or biomolecules can form on Titan, they basically simulate that for Titan. And I've seen some of that apparatus that turns completely orange. I know a lab at NASA Ames that does that, and they have a really hard time cleaning up their apparatus after they do these studies. At JPL, there's the Life That Does Origin of Life studies. They actually simulated something like hydrothermal vents, and they created these iron oxide colonies in apparatus that is similar to Miller-Urey experiment to study what kind of complex organic molecules can form around these. And that's a picture that's taken from the lab at JPL. So they had a hard time creating this iron oxide column right there. But yeah, you get to see interesting chemistry, and you can see that the water colors have turned different. Eventually, when you start the experiment, the water is clear water. So it's DI water, so it's always clear. But once you run the experiment under that electric spark for a certain number of days, then you start to see the change in the water color. And then when you analyze that, that's when you start to detect complex organic molecules. So this is the kind of ancient chemistry that could have been happening in early Earth or in the Hadean Eon, which eventually led to the formation or the prebiotic conditions that led to the formation of the first cell, whether it happened on Earth or it was panspermia. That remains a nice debate. But yeah, we did have interesting chemistry going on. And this also helps us, studying about ancient Earth actually helps us study other planets and what chemistries are happening on those planets and planetary bodies when we go for life detection missions. Because it helps us design instruments that, okay, these are the molecules that we want to detect on so-and-so planetary body, because that's what our experiment tells us, that these conditions will produce these organics in such conditions. And then we see whether those organics are interesting biomolecules. Can they actually lead to some kind of origin of a cell, or some kind of process that will eventually lead to formation of life? So the final segment, plate tectonics elsewhere. Earth, by far, is the only known planet where we know plate tectonics is happening, and we know we do not understand all of it, but we know most parts of it. And excuse me again, I'll just take a sip of water. However, the recent InSight lander mission from NASA on Mars has a seismometer which detected earthquakes or earthquake tremors taking place on Mars. And that basically told us that there is some kind of plate tectonics taking place on Mars. Also, they discovered that the crustal thickness of the hemispheres between the different hemispheres of Mars is different. The northern hemisphere crust is actually of a different thickness than the southern hemisphere. Excuse me. And on the left, you're seeing a picture. Excuse me. On the left, you're seeing a picture that's taken by the European Space Agency's Mars. Excuse me, Siddharth, can I take like a half a minute break?
Absolutely, absolutely. Take a break.
Okay, I'm losing my voice. I'm just going to get some.
Yeah, that's all right. Until then, I would just like to tell everybody that maybe if you have questions, you can start listing them in Q&A. We've already got over 60 questions. So we'll obviously not be able to handle 60 questions in the time that we have remaining. But what we are doing is we have tasked the teaching assistants to note down all of the questions as well. So let's just have everybody take a couple of minutes. Afshin's been talking for a really long time. It's been such a great talk, Afshin. I think everyone's hooked in, and we also have a lot of people who ended up joining a little late, but I think they've all caught on. So this is great. I think this is going fantastic. Hi, Jen. You want to offer some comments while Afshin takes a bit of a break?
I wasn't planning to, but no, I'm really enjoying the talk. And especially as an earth scientist, it's always wonderful to hear. I mean, I'm so comfortable in this this discipline, so it's wonderful to hear someone else's perspective. And I've really enjoyed it a lot. I have been glancing occasionally at the Q&A, but really I've been paying attention to the talk rather than answering questions. But I have seen a lot of good questions that have come in, and just like yesterday, they're usually questions that you can't give a 10-word answer to. They require discussion or a paragraph, and so.
That's cool.
But everyone, thank you for your questions, and I mean occasionally there's one that you could Google the answer to, and I encourage you to do that. But otherwise, no. And this notion of, do we have plate tectonics? I mean, gosh, she's taking a break right at the she's leaving us with a teaser of where might we find plate tectonics in our solar system. We've seen people. Here she's back. I won't comment any further. I'll let Afshin take it away.
Thank you for bearing with me. This is I apologize, but I'm losing my voice.
Great.
No, don't apologize.
It's great. When you were drinking on camera, it looked, you couldn't see your water bottle, so it looked like you were drinking an invisible solution.
That's because I'm in a galaxy far, far away.
Are you? How are you, Afshin? Are you okay to go?
Yeah, I'm okay to go. Can you see my screen, everyone?
Yes, it's on.
Okay. So interesting things have happened in recent times, and we have evidence for plate tectonics on Mars. Excuse me. Although it's not like Earth, or we are not seeing any active subduction right now, but we are seeing these fault zones that you can see in this image by the Mars Express orbiter, and we are seeing seismic activity on Mars, which is very interesting. So just know that it will take some time for us to understand the kind of plate tectonics that's taking place. Also because Mars, yesterday John talked about the difference in how Mars and Earth went on completely different trajectories, even though their ages are very similar, but the process of differentiation of those three distinct layers that happened on Earth did not really happen on Mars. And that's something else that InSight is actually also studying. It's studying the temperatures the ground temperatures and the rock temperatures in which they formed. And it's also studying something along the forms of differentiation that took place on Mars. It wasn't as well defined as it is on Earth, where you had all the densest elements sink to the center in the core, and then the less dense and the least dense and the crust. This did not take place in Mars. And that has also led to the cooling down of Mars. Also the loss of magnetic field also tells us that the core has cooled down a lot. So it's not as similar to Earth. So the engine which drives plate tectonics will obviously not be very similar to Earth, but it's interesting to find that they're still finding evidence of plate tectonics on Mars, which is very promising and exciting for everyone who's a Mars enthusiast, including myself, because plate tectonics is one of the key driving forces, or I would say the geological reasons that first is differentiation, in my opinion, and then plate tectonics that really makes a planet become habitable for 4.5 billion years. So I think from a geologic point of view, these are processes that are interesting when we are looking for life or when we are thinking about making a planet habitable. So that's what's happening on Mars. Now, because we talked about volcanoes, there are volcanoes on Venus, and somebody had asked about it yesterday, so I thought I'll put this slide in. Yes, there are volcanoes on Venus, and what we see on Venus is something called a runaway greenhouse effect. That's because when the energy that's being absorbed by the planet from the sun becomes high and high and gets absorbed, and it's not reflected back into space, it causes the atmosphere to become really, really hot. So that's because of the excessive amounts of carbon dioxide that has been released by these volcanoes. And that's an image of lava flows on Venus. There is no evidence of any plate tectonics on Venus. And for Venus and Mercury, for most parts, planetary geologists believe these are planets which have a heat source inside, but their crust or their lithosphere is much more rigid. And it's not similar to Earth, where it's broken up into plates and then those plates are moving around. So there's no subduction taking place or no sinking back into the inner portions of the planet happening. But there's volcanism, certainly. And like I said before, volcanism can also happen because of mantle plumes. So that's probably what's taking place on Venus. And because of that excess volcanism, because of that excess amounts of carbon dioxide that has accumulated in the atmosphere, it has led to Venus becoming really, really hot and hostile to life. So there are astrobiologists who would like to study and understand what possible life forms could exist on Venus. But just if we are thinking in terms of setting up a human base, then Venus is not the ideal place for obvious reasons, because of the toxicity in the atmosphere and the gases that are there and of the extreme temperatures. But it's an interesting place astrobiologically if we are trying to understand all kinds of lives that can evolve in our solar system. So Venus is a good example, and usually I use it as an example whenever I teach climate science to students, that, hey, if we don't do anything about climate change, then that's our future, that excessive amount of greenhouse gas in the atmosphere and the superheating of our planet, that's where our planet will head to eventually if we don't take climate change seriously and don't take active measures to stop putting greenhouse gases in the atmosphere of our planet. But otherwise, our planet will eventually probably cool down and become like Mars, which is also barren, by the way. So another interesting place in our solar system where geologists discovered some evidence of plate tectonics, and that's why the Europa Clipper mission was born, which is now currently being prepared at JPL, which will go and look for some kind of evidence that can show either ice shelf subducting or going under the other ice shelves, or any kind of plumes that are pushing up any material from the insides to the surface. Some of the reasons were, of course, the computational models, but then what was observed on the surface of Europa. So Europa is an icy moon of Jupiter, but we don't notice any impact craters in there. When you study moons or any planetary body in the solar system, essentially, if there's no surface process taking place, something like erosion or plate tectonics or whatnot, then you will always see impact craters. Like, for example, our moon. If you look at our moon, images of our moon, you see all these impact craters that has taken place because of the various meteorites and asteroids impacts, or rocks, space rocks that impact upon the surface. But Europa doesn't have that. It obviously has some surface process going on. And then you see all these dendritic formations that looks like, recently it was discovered, it was some kind of an internal source that is pushing up some material from the bottom to the surface, which flows on top. For a certain period of time, which has led to the creation of these dendritic patterns on the surface of Europa. And again, the absence of impact craters, very, very strange. Of course, many geologists have also argued that it could be because of the gravitational pull of Jupiter, because if it's a gas giant, and because of that, maybe enough impact is not being created on one of its moon. Yes, all of that is there, but they also found evidence that ice shelves may be having a subducting-like motion, and this is taken from one of the papers on Europa's tectonics, the paper that proposes Europa tectonics, where they are assuming that there's some kind of more dense plate ice shelf basically subducts under the less dense ice shelf underneath, and also pushes up some material towards the surface. So Europa may have plate tectonics, maybe not like Earth, because of obviously these are ice shelves, but it is having some kind of plate tectonics. And again, that is very interesting to both geologists and astrobiologists, because they are also eventually planning to look for signs of life. But right now, Europa Clipper mission is designed mostly to study the geology, the chemistry, and the energy systems that are driving these surface processes or these plume processes that are taking place on Europa. This will not be a life detection mission. So just in case people who are excited about Europa and you were thinking that, okay, we are going to go look for some octopus-like creatures inside of the subsurface oceans in the Europa, but it's not going to do any of those things. It's going to look for active geology and active tectonics, which is really, really important. Just to give you an example, for Mars, we've been sending rovers to Mars, or NASA has been sending rovers to Mars since the 1970s. And only now in the 2020 mission do we have a robotic astrobiologist, which was launched, which will actually look for biosignatures. Prior to this, it was always just studying the soil chemistry and the geology, the atmosphere, and everything else that is very important before we really go and try and determine which are the areas where we can go and look for life signatures. So yes, Europa Clipper, it's a very exciting mission, a very important mission, but it will mostly be looking for evidence of tectonics, studying the energy systems and studying the geology, and then determining what the future Europa missions, which areas should be explored more. Other planetary bodies that may have plate tectonics or plate tectonics have been discovered. Enceladus is another candidate where they think similar kind of tectonics is taking place, where you have ice shelf subduction taking place underneath that icy crust. Io, I did not put a picture of Io on there because Io, we know for a fact that there's no plate tectonics taking place, but the volcanism is happening because of the gravitational interference and because it's locked in a very energetic field with other planetary bodies or moons close by to it. We know there is some kind of tectonics that has happened on Pluto and its moon Charon, and it's more an extensional tectonic deformation, which means that there was some kind of what you see on Earth is divergent boundary, where plates, when plates extend, they move away from each other and creates new plates. So there was some kind of extension that took place, but they haven't found any evidence where some kind of collision and compression or some kind of a subduction zone where a plate is basically going into the interiors of the planet has taken place. So if plate tectonics has happened, or plate tectonics that exist on these two planetary bodies, it's definitely not similar or nothing like Earth. But there is some evidence because of the geologic features that have been studied so far on Pluto and its moon Charon that tells us that there has plate tectonics has led to the creation of these features on these planetary bodies. So that brings me to my concluding slides, and I would just like to reiterate some of those points that I covered today, is that the takeaways should be that plate tectonics definitely provided us conditions to make our planet habitable and sustain life for billions of years. So it's definitely important. It plays an important role in habitability of a planet. Whether it plays a role in origin of life or not, that remains to be seen. It will be determined if we find life on a planet that does not have any plate tectonics, then we can say that yes, we don't need it. But yes, relative motions, regeneration, recycling of materials, all of this is very important to sustaining life on a planet for these many billions of years and reshaping the surface of our planet. It also plays a role in modulating the temperature and long-term climate. So it has played a much slower role along with the position of our planet around the sun, which is part of the Milankovitch cycles. That's a whole different climate cycle talk. But just remember that plate tectonics also plays a role in modulating the atmosphere and long-term climate. Also because volcanism is associated with plate tectonics. So yes, if you have too much of volcanism going on, then that is gradually giving up a lot of water vapor and carbon dioxide into the atmosphere, which changes the long-term climate. And plate tectonics enables the recycling of materials. So if the recycling, we talked about the carbonate silicate cycle, if this recycling of material wasn't taking place, maybe our oceans may not have been so hospitable to life as life evolved and thrived in the oceans as it does today. It may not have happened in the absence of plate tectonics. So with that, I thank you for your patience and attention, and for patience for when I took a short break to drink some more water. But yeah, this concludes my talk, and I'll be happy to take some questions. So over to Sid.
Thank you so much, Afshin. You can relax and take a breather now.
Okay, I'm good to answer some questions for sure.
Awesome. All right, so we're actually quite, in fact, slightly over time. So we won't be able to do questions for obviously everyone. I see there's a lot of questions, which clearly indicates that there's a lot of interest and excitement about this topic. So that's great. So let's do this. Let us just, we'll have to select, say, 10 questions. And then give justice to them and answer them properly. And then what we'll do is we'll take down all the other questions and we'll try to answer all of the questions, offline. So we take your head to do that. And I'll ask the PAs that they can just get like a couple lines from you for each of those things. So let's do that. Sure. And we'll try to do this over the next 10 minutes or so. So 10 to 15 minutes or so. I also wanted to give everybody information on the assessment tasks. So as soon as we're done with the questions, we'll move on to those. How does that sound?
Yeah, sounds good.
Okay, great. Perfect. All right, let's see what do we have. And feel free to also, Afshin, go through Q&A and see if you find any question that is pertinent. I'm just going to select whatever I feel is good. Okay, there we go. So the first question is, how did geologists determine the boundaries of the plates?
Geologic boundaries. So that has been done over the years with extensive surveys. Of course, surveys of the ocean, like that was one example that I talked about when they started studying the ocean floor. They were able to determine the divergent boundaries that exist in the ocean floor. And then, of course, they started to understand what was happening on the other side of the boundary where convergence is taking place. And at convergent boundaries, you're able to mark these boundaries wherever you have trenches. That's where you have two plates coming together, and then one is actually undergoing into the mantle, and the other one just uplifts and creates mountains and volcanoes. So that was another way of geologists determining these boundaries. For, say, something like Himalayas, where you have large mountain ranges, or say Alps or the Appalachians here in the United States, these are places where you have mountain building events that have taken place. So this helped in knowing the geologic history where continents had always moved around and come together. So when we know that continental crusts come together, you will have accretion of rock material and upliftment of that rock material to create these mountain ranges. But then these mountain ranges are not there by themselves. These mountain ranges are highly faulted zones. For example, Himalayas, it's a very highly faulted zone where you constantly have movement along these fault lines, which leads to these earthquakes. For example, the last major earthquake in Nepal caused the subsidence of land along that fault line where the earthquake took place. And there was major destruction in the village where this took place. So this tells us that this is where basically different land masses once upon a time came together and jointed and uplifted. So, but that joint, that has not glued, that's still, there are still fault lines there where they have jointed together. So these geologic features have helped geologists determine or create a better geologic map of all the plate tectonic boundaries.
Mm-hmm. Thanks. Next question is from Nasrullah Masood. He asks, how did the rotation of Earth contribute? Was there any contribution from the planetary rotation to the drifting of the continents over time?
Not that I know of. The movement of continents or the movement of plates is really being driven by the Earth's convection cycle happening from the inside. And I would ask the panelists, I guess Jen or John, if you can correct me if I'm wrong, if you know any evidence or any studies that have been done that showed that the Earth's rotational motion caused the movement of plates at all.
Jen, any comments?
No, it's generally, at least I've generally assumed through discussions that it's not a big issue. There has been a lot of debate whether or not, is it the push and the uprising or the pull me of essentially the sinking of the subducted slab. But I guess over the past decade, people sort of concur, as you mentioned, that it's the buoyancy and upward cycling that's driving the activity coming from the mantle, or sorry, coming from the core. Heat transfer.
Mm-hmm. Okay, thank you. Let's see, next question from Archie. Is there any evidence of volcanic activity on Mars?
So interestingly, the tallest volcano is on Mars, Olympus Mons.
Yeah.
We don't have any evidence of any current volcanic activity. But I will not say anything. I will just leave that question open-ended, because what if I say we don't expect any volcanoes to erupt on Mars, and then 10 years down the lines we have an astronaut who goes there, and then we measure some volcano is suddenly becoming active, then I'll look bad. But no, there has been no evidence of any recent volcanic activity. InSight actually just detected earthquake tremors, but it was not associated to any active volcanism on Mars. And mostly because interiors of Mars has cooled down a lot. So we don't even know the extent of how much molten magma is there that can, come up and rise up to the surface.
Okay, thank you. Another question is from Payal Pawar. She asks, can global warming affect the formation of hotspots, earthquakes, and tectonic plate movements? So does the atmosphere, the changing climate, does that have an effect on the movement of tectonics? Is there any evidence for that?
Not hotspots, it's actually the reverse. So eruptions from hotspots and movement of tectonic plates actually affects global warming. And in the past, the different ice ages and climate change plate tectonics has played a role. For example, if you imagine Pangaea, and I've stopped sharing my screen, but everyone remembers that giant supercontinent. Pangaea had very different climate conditions than what we see on different continents today. The center parts of Pangaea were extremely, extremely dry. So moisture-laden winds could not even reach some center parts of Pangaea because of mountain ranges that existed in the way, and most of the precipitation was felt by other parts or outer parts of Pangaea. So once those places split apart, then those drier regions started to experience monsoons, because once they were in the center of Pangaea, they were not getting any rainfall. And then now all of a sudden the continent splits, and now they are by a coastline. So they are getting more of rainfall. So yes, long-term climate effects have been affected by plate tectonics and hotspot volcanic events, but not the other way around.
Okay, great. Next question is from Lisa Marie Prasad. She asks, how much does our moon contribute to volcanism on Earth?
Moon contributes to the tidal forces in the ocean.
Yeah.
We do not have any evidence that the moon affects volcanism. Volcanism, if you study it as a geologic event, then it has a lot to do with what's happening inside of that magma and the temperatures at which the magma is forming. And even with volcanism, like I gave a very, very broad view of volcanism today. So it's not like the plate subducts and one fine day it decides to just rise up from the volcano as magma. It takes a long time for that magma to actually build up inside of the volcano. And it kind of builds up like a pressure cooker. The pressure system builds up inside of the volcanic cap. And then once the magma chamber has enough pressure built up, then it goes up in a big boom, and all of that molten magma comes out. So moon does not have any kind of effect on this process.
Okay.
Or at least we don't know of anything. I'm not even sure if anyone has explored that.
Yeah, thanks. I think that's a fair answer. I haven't come across any studies myself. Jen, do you have any thoughts on that?
No, I think you gave a good response, Afshin.
Okay.
But it's interesting, though, thinking about how, as you mentioned, the moon pulls the tides. So it'll have bigger differences in the tides with a full moon or when the moon's closer. And it could be that there is some correlation between volcanic activity or movement of magma, earthquake tremors. But to my knowledge, no one's ever looked into that. It'd be sort of a small effect. And it would be an interesting thing to do.
Also because of, it revolves around the planet so fast. So like it goes around in 29 days, it will need more of a longer term effect probably to have an effect on magma.
Perhaps in systems such as Pluto and Charon, there might be some kind of an effect.
Yeah, and Pluto and Charon, one of the reasons why Pluto was demoted to a dwarf planet is because the moon, it actually waltzes around with its moon. So it's not like Pluto is stagnant and then Charon is going around it. It's actually both of them waltzing together. And that the Astronomical Society decided, okay, that's something they don't like. So if a planet is also dancing around with its moon, then we just call it a dwarf planet. And the size, of course, whatnot. So yes, so Charon and Pluto, maybe they can affect each other in different ways in their geological processes.
Okay, so I'm going to take the last question just in the interest of time. So the question is from Jen James. He asked, ma'am, you said Europa shows no evidence of impact craters. Just to guess, could it be due to the surface being primarily ice? Any such impacts get and don't remain so because ice would cover up or melt or refreeze, thereby filling up the crater? So the question is, how do you really determine on a surface that is primarily ice if there is evidence of impact craters?
So impact craters, even on icy moons, for example, Enceladus has impact craters. If I go back to my image, again, Enceladus has impact craters in its image. Or if you're sitting on a computer, you can just quickly Google Enceladus and it'll show you an image which has impact craters. But you don't see that on Europa, and that's a very curious thing. And that has led geologists to believe that there's some kind of other surface processes taking place on Europa, which is associated in some way with plate tectonics also. And that's why you don't see those impact craters.
All right.
Because Enceladus is also an icy moon, but you see those impact craters on Enceladus.
The surface. Okay, thanks, Afshin. I'm going to end the Q&A session just because we don't have enough time. There will be for sure more good questions that have been asked. We haven't only picked out the best questions, we're just scrolling through whatever was there, but we will make sure that all the questions reach you and we're able to get the answers out to everybody. So thanks a lot, Afshin. Thanks for doing that.
I look forward to it.
Thank you. And okay, so what I will do now is I just have one slide where I wanted to tell everybody about the assessment tasks. So let me just share my screen real quick. Okay, can someone confirm if you can see my screen share?
Yes, we can.
Okay, thank you. So there's primarily three things that everybody needs to do after each class. There's three Google Forms really that you need to fill up. And I'll go through each of these Google Forms that need to be filled up, and they will count towards your participation as well as course completion for this particular course, right? The first being the analog site assessment. Now, you all must have heard a lot of references to places on Earth that help us understand different regions in our solar system. They could be geological, they could be similar in ways of the microbiology that exists there, the atmosphere that exists there. So as you're going through this course, we want you to be able to contribute towards the creation of an atlas that we are putting together of all these analog sites that exist on our planet. And to do that, we will be offering you a particular site on our planet, and you have to basically you have to fill up that Google form, go through it. It's like a simple form that you fill up. You start off with your name and email, and we'll have a quick demonstration of that as well. But you basically have to grade it according to different categories. So you have to help us determine how good is this region for terrestrial analog work, right? And towards this, we have categories and subcategories. So for example, in terms of science, engineering, logistics, and safety, and within each of these categories, there are several different questions that you will be asked, and then you need to grade it between 0 and 5. The one thing to keep in mind is that this is not a quiz that is like a right or a wrong answer, right? So it's a very subjective assessment task that you're filling in, and it's basically assessing your observation skills, how well you're able to observe images of a particular site, how well you have taken back information from each of these classes, and your ability to reason based on what you're seeing, all the information that is in front of you, and you need to grade it. So there will be definitely a range of responses that we will be getting, and it's basically us trying to also get a sense of an understanding of how you all are able to get the information from us and see what is available out there, and then answer and give us that information back. There will be many terms in there, certain categories and subcategories, which you might not immediately identify with. So towards that, we will encourage you to read about those particular terms, read the uploaded material that we will be putting up. We'll be sharing some papers that will help you assess how different analog sites have been graded in the past. For example, to select a landing site on Mars. So what are the different sites on Earth that are helping us understand where should we be landing on Mars, for example. So, and you will be having time. So it's not like we are expecting you to hand it in right away. We'll be giving about 2 weeks for each of the assessment forms. In case you need more time, we'll also allow that. But the initial deadline is about 2 weeks that everybody has to fill it in for. And there'll be a total 3 such assessment forms for the analog sites. The second form of assessment is a Google form on identifying. You basically have to identify 3 keywords. So we've already had 2 lectures so far, one from Dr. Jonathan Clark and the other from Dr. Afshin Khan. So if you haven't been already noting them down, I encourage you to go back and watch the recordings and identify 3 keywords in astrobiology that you found and come up with the definition, or not come up, but rather look for and study and come up with a definition for those particular words based on your reading of the description of whatever word you have identified, either through the reading material or online. And then you just have to give us those words. And the reason we are doing this is basically we are creating a glossary for astrobiology. So it will be this one large database that all of you will be contributing towards that will help us identify all of these important words in astrobiology that we can then, once the glossary is ready, we can then hand it over to anybody who's coming in new who wants to learn about astrobiology. So it'll be a great education tool, and it'll also be a chance for you to contribute towards the learning of astrobiology. And the last one is a feedback form. So this is more for us, but it'll also help us assess your engagement in the class. We need to know how well we have done, and we'll be having these feedback forms that will be circulating after each class. So for example, after this class, you will have to fill in 2 Google forms. So one for this class, and then the previous one that was held yesterday. And then similarly from the next week's class onwards, we'll have similar such forms. So all in all, there's going to be 3 forms that need to be filled in after each session. And for yesterday's session, of course, we'll be clubbing it and then sending it to you together. So you'll be having to fill in individual forms for each of those classes as well. And we'll be sending out an email to everybody, because I've identified there are many people who are still not on Google Classroom. That will have a complete walkthrough as to how exactly and where you can find these forms and the links for these forms as well. So if there are any questions to that, don't post them here. We'll try to have all the information out. And if you still are not able to understand what exactly we are asking of you, then you can let us know about that. So that was it from my side. Maybe Anurup, very quickly, if you can share your screen and we can give them a demonstration of the form.
Yeah, 1 second.
Okay, so this is a sample form for a particular site called F Mars. So, we will not give you all the information. We encourage you to go online and search where exactly this place is. You can see something like a Mars habitat that has been set up. So where would the site be? So it's all up to you to find out that information. But what we're really looking for is you'll be clicking on the Google form. It will open up like this. And then if you scroll down, you'll have to fill in your email address, your full name. You'll have to indicate whether you saw the lecture live or recorded. That is just for us to keep track of how many people are watching this offline as well. And if you click next, so there'll be several categories. So like, for example, like I mentioned, scientific. So if you had to assess this particular site in terms of how relevant it is for conducting, analog work, the question is how Mars-like is it? And then there's a word written there called geomorphology. So there's some words that have already been spoken about in today's lecture and yesterday's lecture. Some of them have not been. So don't worry about it. Read about these words, try to find more information. And once you have a general idea, you just have to grade it between 0 and 5, where 0 means it's not at all like Mars. There's no resemblance. There's very little or no negligible geomorphological, resemblance to Mars. And 5 being it has considerable relevance to Mars. And similarly, paleontology, you can grade it, and microbiology. So you do the same. Then you click on next, and you do the same for engineering. So we encourage you to browse the internet and find as many images as you can about these particular sites. We have selected places where there are enough images and videos as well for these sites. So you should not have a problem getting access to that kind of information, and as well as papers that have already been published about these particular places. And then also temperature variations. So all of these are important categories that actually help us assess how well we can conduct our science and engineering research at these particular places. You go next. Unwanted visitors, obviously very important. You don't want to do your analog research at a site which is continuously being disturbed by people coming in and disrupting all the work that is taking place. Infrastructure is also important because you want to set it up in a place where you have access to roads and water supply. Potential health issues. You don't want to be in a place which is dangerous for you for doing work. And Anurup is just filling in random numbers, so you don't have to fill in the same exact. You don't have to grade it in the same way. Because, like I said, there's no right or wrong answer. It's all based on your assessment, and that's something we're looking at. Aesthetics is also important in several ways, especially when you're trying to do some work that involves the visual aspects of the particular location. So color, the presence of surface water. Now this was in specific reference to Mars. So an analog site doesn't always have to be representative of Mars, but we'll indicate it to you. Like for example, if we are asking you in terms of Mars, so you'll have to grade it according to Mars. Okay, and then in the end, we also have given you an option to suggest a site. So aside from what we have already indicated as a particular site, we encourage you to look around you in your region, in your country, wherever you're located, because we're taking advantage of the fact that we have people from 53 different countries right now. So there must be many sites which have still not been identified. So based on all of these different criteria and all of these information that you're reading, you might be able to help identify a site which has never been heard of before. So we encourage you to do that as well. Indicate the region, the site, and the country, and then you just submit the form, and that's it. So that would be the way to go. And similarly, I'm sure you'll be able to fill in the other Google forms for the feedback as well as for the glossary. So that's mainly the way in which we are trying to ensure that this course is engaging. we're also trying to ensure that all of you are able to contribute towards the ambition that we have here of creating this community of astrobiology. And it only starts with a team contribution task. So that's basically it from our side. So let's close this very nice lecture that Dr. Afshin Khan has given us today. I encourage all of you to read more and more about plate tectonics and the importance that they have played a role. So we've received the background information, the geology, the movement of all of these different features on our planet. And next week, we'll be going into the biology, that how did life start? Where exactly did it start? How did it start? All of these are relevant questions that Dr. Michael Macy will be taking up. So I hope you've all got a chance to get a teaser of what this exciting field of planetary geology is all about and what relevance that actually plays. It's the precursor to how life actually can start and how a planet is actually made habitable or not. So with this, I would like to thank Dr. Afshin Khan. I'd like to thank all the other instructors who've been with us throughout the session today, and all the teaching assistants as well. And to all the participants who are joining us from all around, we're really, really honored to have you with us. And we'll make sure that you're able to get access to all the information. If there are any questions, feel free to post them in the Google Classroom comment section. Also there's WhatsApp and Slack groups that have been informally operated by the students, so you can all talk amongst yourselves as well. So thank you very much and have a nice evening or day ahead based on where you are. Thank you. IT, I request if you can please stop the recording.